case 2, you probably want to correct the definition.
So I already got my grade for it. Can't go back in.
You have not divided. So case 1 you have to choose the steps. Case 2 you choose these. Okay, that was an assumption. I definitely didn't even realize that I just
So what I think the problem because I actually worked with pesticides, I know that. So is it as for my
I didn't finish the algorithm somewhere. I mean, I have lots of suggestions. There's usually like actually probably one of the best things that I've ever done. Oh, I'm not sure exactly where it is. Oh yeah, I don't know. I was gonna recommend it's a I love that. Oh my god, savory, spicy, and like the cinnamon. Oh, I saw that. I was on the sublet. My sister is and so I was sort of surprised at how young, like I thought it would be more. There are lots of crowds in the first year.
yeah, I agree.
Yeah, so these are the ones which don't really have So I think he had some issue one of the days last week.
Yeah, right.
So you have to combine them into part 1, part 2 and stuff. Alright, let's start. So I wanted to start with a couple of announcements. Okay. So hopefully all of you have seen your grades for homework 1. So you announced them, right? Okay. So if you have questions, these are the people you should ask. And the TA is graded question by question. So if you have a question about a certain problem, go to the corresponding TA. So that's the others will not be regrading stuff. So this is just to ensure consistency across everyone. Okay. Now the second announcement, I guess all of you know, homework 2 is due today. Okay, so it's maybe some of you had questions asked me before. So one main thing I wanted to do today is ask if the scheduling for the final. So I've been getting many questions about when the final will be. So the plan is to have it on December 13th. So this is the finals week, and to have it during class. Okay, so it will happen here. I think there are enough chairs here that you can even have some separation. Okay, so if anybody has serious problems in the sense that they cannot make it, then let me know. So. Okay, so Tuesday, December the 13th, class time. Okay, so it will be. So does anyone have class right after this? Okay, so what time does it start? 12:25. Okay, so we'll have to end by then. So the machine learning class officially ends at 10:30, right?
Yeah.
Yes.
Okay, so we can probably start. If you guys want something like, I want to have a 1.5 hour slot so that it's not like 1 hour 20 minutes or something. So I'm just trying to push the limits a little bit. Okay, so we can start from 10:40 to 12:10. Is that okay? Actually, the actual slot, is it 1.5 hours or is it 1 hour 25 minutes?
1 hour 20.
Yeah. So let's tentatively have it to be this. Okay, so we could be 45 to 12:15 or something.
But to inform, on 12th of December is our last class, daily class. We have this class on 12th of December. We won't be having class.
Alright, this is the finals week. Okay. No, but the others might have finals at the same time. So
They don't, the school schedules them, don't they? So that they're not, never, none of them at the same time.
so that is true for undergrad class. I don't think it's true for grad class. So for instance, I don't have any. So it's up to me. So I can have.
That was true for data mining last year. Because I was an undergrad.
Yeah, you should.
Okay.
You should have a schedule.
Yeah, you should have scheduled finals.
Okay, so they didn't. Okay, I'll check again, but this is the impression I had. Okay, so yeah. So let me get back to you guys about this. And the other thing is topics for project. Okay, so list of papers will be out next week, and I'll also have a sample write-up. Okay, so as I said, the project will be, you have to write 2 pages about some paper, about some research paper, and basically it should involve the main idea, some background on the problem, and if anything, maybe the subsequent work and so on. Okay, so I'll give a sample next week. Okay. And you can have pairs. Okay, so you can pair up. Yeah.
Didn't you say at the beginning? I thought I remembered you saying we could also potentially do an implementation of the algorithm described in the paper instead of writing.
If you really want, you could instead of doing a write-up, you could either have an implementation with a real data set where you ask me beforehand.
Okay.
Okay, so this is the default.
Got it.
If you really want something else, we can try to work around. But I would guess that most of you would just prefer this because it's somewhat of I mean, it's easier to do than implement. And so another final thing is about homework 3. Okay, so unfortunately fall break falls in between, so I wanted to give an extra day, so it will be due the Friday after fall break. Okay, so it's slightly off schedule, but just keep this in mind. It will be out today or tomorrow, and it will be due the Friday after.
And will that be released tomorrow?
Yeah, today or tomorrow. So I'll try to do it today, if not, I'll do it tomorrow. Okay, so any questions about the announcements? So the final, I will see if they already scheduled something for me, but they haven't told me, so I'm assuming not. So, okay. So otherwise, yeah.
Heads up on the final exemption should be released the next day.
Oh. Oh. All right. So these are the quick announcements. So any other questions? Yeah.
So the fall break, when you say Friday after fall break, is it the 14th, October 14th, which is during the fall break? Or
No. It's 21st.
Ah.
Yeah.
You proposed in the previous lectures to have a review class before the full break.
Yeah, so next Thursday I want to do a little bit of review and also go over this project. Okay, so might not do it for the full class, but a big chunk of the class. All right. So last class we saw a basic introduction to shortest paths. Okay, so we saw that we saw how you started off with this case of all edge weights being non-negative. Okay, so in this case there was no distinction between directed and undirected graphs. Okay. The reason was that you could change any undirected graph into a two-way directed graph. Okay, and this was fine. Okay, so you could go from an undirected graph with edge like this to a directed graph with two edges. And so this way we always focused on shortest path algorithms for directed graphs. Okay? And when all the edge weights are bigger than or equal to 0, then you could go also from undirected graphs to directed. And we saw Dijkstra's algorithm, which is one of the classic algorithms, all of you should know it. And we saw this data structure of how you maintain a priority queue. Okay, and we implemented it using binary search trees. Okay. Then we started off with what happens when you allow negative edges. Okay. We said that it's a big problem if you have negative weight cycles. Okay, so a cycle whose sum of the weights is negative. The reason is that then the notion of shortest path is not defined. Okay, so you could have minus infinity loops. Okay, so you could just take the loop multiple times. And if you have no negative weight cycles, we started talking about this algorithm which is called the Bellmanford algorithm. Okay, where the main idea behind this was so we observed that if you have a shortest path, it must have length smaller than or equal to n. Okay? Because if not, then some vertex must be repeated, and that means that there was a negative weight cycle. Okay, so that was the argument. And the idea here is it's a dynamic programming algorithm, and we said that you keep track of this quantity, which is distance from A to a vertex B. Okay, so for every vertex B, we keep track of this for every K. Okay, so K is the number of hops, and formally this means the distance from A to B. Okay. So this was the quantity we saw last time, and then we said that you can keep track of these things, and you can just run a basic dynamic programming algorithm. And, yes. So do you guys want me to just go over this algorithm again, or was that clear from last time? Yeah.
Can you go over again?
Yeah. So let me quickly recap it. So this is the quantity we will maintain. If you think of it as a dynamic programming table, then we'll start filling this table up. And the recursion that we are using is, so you have A, and you want to get to this vertex V using K hops, right, at most K hops. The only way you can do that is if you get to some neighbor of V, let's call this U, using K minus 1 hops, and then go from V to U. Okay. So this is K minus 1, and this is the last hop. And we wrote a recurrence for this. So min over U such that UV is an edge. So WUV is the weight of this edge. Okay, so from here to here the path had length being dist of U K minus 1, and then this is the weight of this edge. So this is the recursion we had last time, and now you can start off by filling this table. Okay, so when K is 0, then when K is 0, this A of Vk, this is 0 for V equals A and infinity otherwise. Because you can only reach A using a hop of length A. So this is the base case. And using this we can fill out this table. Okay, so first fill it out for K equals 1, then for K equals 2 and so on. Okay, so how long does this algorithm take? To answer this, you've got to analyze how long does it take to filling out one K, right? So the table for one value of K. Like suppose you computed it for all K less than this value. You want to compute it for a specific K. Okay. So how long does this take? So is the question clear? So in the algorithm, the way we are computing it is we have K equals 0, which you initialize. Okay, so this is the initialization. K equals 1. You are computing just A of the first vertex, then V2, and so on. Right? So how long? So how long does finding each of these entries take? It's the in degree of this vertex, right? So this is what we said last time. So we are taking a min over a bunch of quantities here, and the number of quantities is the in degree of this vertex V. So each step takes in degree of V2. So computing this for V2 takes in degree of V2 time. And what's the sum of the in degrees in a graph? Yes, yeah. In undirected graphs, yes. In a directed graph, if you only sum up the in degrees, it's exactly the number of edges. So this is, these add up to number of edges. So each row of this table takes E time to compute. And how many rows do we want to compute? And what's the largest value of k that we are interested in? Yeah, it's n because we said that you only have to consider paths of length up to n, okay? Because there are no negative cycles, so the shortest path always has at most n hops. So k less than equal to n. So the overall running time is O of n times e. And so this is okay, this is not very good, but this is what this gives. Okay. But the nice thing here is, so note that Dijkstra was only O of n plus e times log n. Right? So Dijkstra is often much better than this, but this handles a much general case. Okay, so this handles negative weighted. Okay. So this handles negative weighted. So in the homework you will see that you can try to make Dijkstra handle negative weight edges, then you could have exponential learning time. Okay, so we'll see an example of that. So this is one of these well-known examples, but it's good to do it in a homework because it's good to know. Okay. All right. So the next thing I want to do is, so I want to go over this kind of quickly, which is, so far we've been considering shortest paths always starting from a single node, right? So I wanted to just talk about this other very well studied problem, which is which is called Allpair shortest path. So here we are actually interested in shortest paths between every pair of vertices. Okay, so you have some graph and have some edges. Okay, so imagine for now it's a directed graph. And for every pair u and v, you want to compute the shortest path from u to v. Okay, so this is an n squared, this is an n times n matrix that you want to compute. And the entry corresponding to u and v is the shortest path distance from u to go to v. Okay. So this is sometimes useful to know. Okay. So some applications in which you might want to find these out. And naturally the question is, can you do this faster than doing just a search from each vertex? Okay. So you can obviously solve this by just using the single source shortest path, by just doing it for every vertex. But the question is, can you do faster? So So suppose to start with all weights are non-negative. Okay. So then what is the target that you want to beat? So what does Dijkstra from each node take? So we know what each Dijkstra takes. So what is
N times.
yeah, it's n times whatever Dijkstra is. Right? So it's n times n plus m log n. So this is and if you assume m is bigger than or equal to n, so this is something like n m log n. So this is non-negative edges. So it turns out this is actually pretty tricky to beat. Okay, so in fact, for sparse graphs, it's not known how to do much better than this. Okay, so something slightly better than n times m is known, but we don't know if you can do significantly better than this. So most of the work, so what we are going to see today is about the other case where we actually could not do very well. Right? So remember in the case where you allow negative edges, if you allow negative edges, then earlier even one source took n times m time, right? Because this is the n times size of E, which is n times m. Okay? So even for one starting point, it took n times E, and now you could ask, can you beat this? Okay, so here, using the previous thing, you get n squared times m, and we are going to see today how you can do better than this. So is the goal clear? For non-negative weights you can't do much, for negative weights you can try to do better. Alright, so I want to do this just to kind of illustrate again, so some of the things that we've been seeing so far. Okay, so suppose you have this kind of a dynamic programming algorithm. Okay, so I want to maintain the same sort of a thing. So I want to maintain so recall this is distance from A to V to U using now suppose I want to now maintain it for different A's, right? So earlier we only cared about a single A, now you want to do this for multiple A's, right? So let's say I throw this also in as the parameter, and I want to maintain these kind of quantities. Okay. So earlier what we were doing was compute dist of A U K using dist of A U K minus 1 values. Right? So for different U's. Okay, so we first computed these for K minus 1 and then we were doing this. But what if you really wanted to just use, can you do it better? Like instead of K minus 1, what if you really wanted to do K by 2? Okay, so can you do something like this? So remember the goal, right? So what is this quantity? So this was, I had to go from A to U using at most K hops. Okay. So now you could say, okay, I will go from A to some other vertex. Let's call this X. Okay. Using K over 2 hops. Okay. And then you can use K over 2 hops to go from here to here. Okay. So why couldn't we do this earlier? So here what I am saying is I can try going from A to some other vertex X. So I'll consider all X's. Okay. And then I want to go from A to X using K by 2 hops and X to U using K by 2 hops. Okay. So you can now write this recurrence. This is equal to min over X in V of X K by 2 x to u k by. So does this recurrence make sense? Any path of length k, length at most k, you can always break it up into two halves, right? Or nearly halves. And you can say that I'll first look at the distance from a to x, k by 2, and then I'll look at distance from x to u using k by 2. So this recursion makes sense. But why couldn't you do this earlier? So earlier we were interested in only things out of A, right?
I mean, couldn't you, there's one on top that's even shorter than this, if you have no direct route.
If you have a what?
You have a direct route between A and U.
Right, but so remember the definition says it's smaller than or equal to k hops, right?
Okay.
So any path, you could break it up into like nearly half things. So that's, yeah. So this is definitely correct. But the question is, why couldn't you have done this before? Yeah.
So we wouldn't have been computing the x to u because we didn't care about that before.
Yeah, so is this point clear? So earlier, we only cared about distances from A. Okay. So we never really stored these numbers. Distance from x to u using k by 2, using just k over 2 hops. So the way we handled it last time was that we had this WUV, which was just the edge weight. Okay, so the edge weight we always had. So that's why you could only use the k minus 1 thing. Okay, so you could not use the k over 2 intermediate vertex. Okay, so think about this for a bit if you don't see this. But any questions? So did you have a question? Oh, okay. So earlier, yeah, so this is the issue that we never stored this quantity. And earlier the amount of memory we were using was actually somewhat smaller than now. Okay, so now we are using n squared times n again because k goes from 0 to n. But earlier we were just using n times n. Okay, so is this point clear? Good. Yeah. So this is the thing that I want to illustrate. And now we have something nice, right? Because what we are saying is you can keep doubling this length. Okay. So you start off with k equals 1, okay, and then you can go to k equals 2, k equals 4, and so on. Okay. So using the values for k equals 2, you can compute stuff for k equals 4, and so on. And how do you initialize these things? Yeah, initialize distances just like we did before. Okay, so it turns out k equals 0 and k equals 1 are actually trivial. They're just the same way as before. So you can initialize these and then you can just use these computations. Okay, so it's very easy to keep repeatedly doubling. Okay. So now if you want to go up to k equals n, you have only like log n different steps. Okay, because you don't really need to do it for every k, right? Because that's the nice thing about our definition, which is that we used, so we are looking at the distance to go from A to U using at most k hops. Okay, so it's not exactly k hops, and this is why you can just keep doubling, and that's fine. Okay. So, any questions about this?
odd number, wouldn't there need to be like an extra step at the end to consider?
No, so you just, so if k is 23, you go up to 32. Okay, so because that's the next power of 2 that shows up. Okay, and that's only at most twice the number, so that's fine.
Okay.
So, yeah, so that's a good question. So always we go up to k being the nearest or the smallest power of 2 bigger than n. And the number of steps is still roughly log n. Yeah.
Why do you go up to the nearest power of 2 instead of going down to the largest power of 2?
Because we want to go up to k equals n. And so suppose the nearest power of 2 was, so again consider n being like 23 or something, then then you only consider paths of length 16 if you go to something smaller. Right? While you want to consider paths up to 23. Because for all you know, the shortest path has length n. Okay, so that's why. Yeah.
So in that case, then you'd be considering a path that's 16 from A to X, and then a path that's 16 from X to U, which is still bigger than 23. So how do you,
Yeah.
how do you pair up those?
Oh, because I mean, we only care about paths of length at most 16, right? So, sure, if you found a path of length 32, it's fine because there are no negative weight cycles. Okay, so you could, I mean, you would actually not have found it because if you really had a path of length 32, then you must have had a cycle. And then removing that cycle would have given you a shorter path. Okay, so you would not have found such a thing. So when you compute this, it will turn out that the paths you get actually have smaller than n length. Okay, because just because there is no advantage in taking bigger. So all you have to verify is that using this, you will consider all paths. Okay. You might consider more than feasible, but those guys actually don't give you any advantage. Yeah, so that's a question. Any other? All right. So this sort of doubling trick is something that shows up often in algorithms. Okay, so this is something you should always keep in your mind. So if you're iteratively computing stuff, then maybe you don't want to do this one by one. Maybe you want to see if you can compute from n to 2n, okay, or from k to 2k, something like this. Okay, so that's why I wanted to illustrate this. And this is somewhat like divide and conquer, which is the title of the slide, because you have a path of length k, you want to break it into two paths of length k over 2. Okay. So one comment here is that I don't think I should go into the connection, but this sort of an update rule, this min over x of distance from a times x plus distance of x times u, it's very similar to what happens in matrix multiplication. Okay, so if you have two matrices, in this case, let's say if you have a matrix A, you consider A times A. Okay. What is the ijth entry of the product A times A? Okay, so A square I only. This is sum over x, A of ix times A of xj. Right? And this is somewhat like this update. Instead of the times you have a plus, okay, and instead of this summation you have a minimum. Okay, so it's like instead of, so this times and you have the summation. So if you replace sum by min and times by plus, okay, you might say, okay, then it doesn't make sense, but then there are actually, you can define an algebra where sigma can be made into min and times can be made into plus. Okay? And then it turns out this is very much like matrix multiplication. And what we are doing in this previous algorithm is it's basically what is called this fast exponentiation. Okay, so if you want to compute a to the power of k, one way to do it is to compute a to the k over 2 and multiply. Right? So what we are doing in the previous step is exactly fast exponentiation. Okay, so that's another cool way to see this. And once somebody makes this connection, the natural thing to ask is, okay, we saw this fast algorithms for matrix multiplication, right? So we saw this algorithm that takes n to the 2.7. Okay, maybe we did not see this. Maybe we just saw multiplying two numbers, but the same kind of a trick can be used. Okay, so this is what is called Stassen's algorithm. So you can actually multiply two matrices in time which is smaller than n cubed. Okay, so if you haven't seen this, you should look up Stassen's algorithm. It's very similar to the kind of algorithm we saw for multiplying two numbers, where you break it up into two pieces, and we had a clever way of multiplying. Right, so I don't know if you remember this. This is in one of the initial divide and conquer lectures. Okay. So it turns out you can do something similar for matrix multiplication. And now you could ask, okay, instead of this n cube algorithm that we saw here, can you actually do something like n to the 2.7? Okay, so this is one of these problems that has that's gotten a lot of attention because, you know, we see that there is a possibility and we want to know if you can do this or not. And it turns out so there are algorithms that do this, but only for, so this one, it's only a limited setting of weights. Okay, so if you have, for undirected unweighted graphs. If you have unweighted graphs, you can do this sort of a thing. But in unweighted graphs, the problem is simple anyway, right? So it's not that big a deal. And this was done by Cyril, but they basically looked at this framework for doing it. Okay. So yeah, so there's a lot of interesting questions around this. And for general graphs with negative weights, we don't know if you can do much better than n cubed. Okay, so that's one of these interesting open problems. Alright, so this is something about shortest paths. So did you have any questions? So we move on to I want to move on to the next graph problem just to give some other ideas. Okay, so let's So the next problem is what I want to call building a communication backbone. Okay, so let's say you have a bunch of cities. And you have some costs of connecting them. Okay, think of it as cost of laying fiber between the cities or something like this. So between every pair of cities, you have something, and let's say the cost here is 2, this is 6, this is 7 probably because maybe there's some mountains in between, whatever, right? So you have this is okay, so you have some network of this kind. And the problem you want to solve is connect all cities. Okay, pick a subset of these links. Okay, so maybe you picked this. So you picked these 4, then you've covered everyone, right? So such that between every 2 cities, so this is what we want. So we want some kind of a way to communicate between any 2 cities. We want to pick as few edges as possible. Okay, so the goal is minimize the total cost of the edges. So, yeah.
So is this every pair of cities, or just that every pair of cities is reachable?
Every pair of cities has a path between them.
Direct. Okay.
No direct edge.
Oh, just
so
a path.
there's a path. Yeah. So, any questions about the problem? So you just want every pair to be connected. Okay, so they should have some path between them. And so this problem has a name. It's called the minimum weight spanning tree. Okay. So how many of you have seen this word before? This phrase? Okay, so most of you probably heard about it. Okay, so what is a spanning tree? Okay, so let's yes, so I wanted to just so what is a tree, right? So I remember when I was an undergrad, our instructors used to emphasize this a lot. It's like tree is not something that has roots and leaves and whatever. Tree is just a connected acyclic graph. Okay, so tree is basically a graph that is connected, which means between every 2 vertices there is a path, and there are no cycles. Okay, so any set of edges that connects a set of nodes and there's no cycles is a tree. Okay, and this is a formal definition of a tree. Acyclic just means no cycles. So note that now we've kind of moved on to just undirected graphs. So the rest of this lecture, think of all my graphs as being undirected. Okay, so if there's a edge, you can, I mean in some sense it's both ways. Okay, and so tree is just this. It's just a connected acyclic graph. So every tree has n-1 edges. Every tree on n vertices okay, so it connects n vertices and there are no cycles. So any such graph has exactly n-1 vertices. So people see why? Just from the definition of being connected, being acyclic. So yeah, it's like a simple exercise. You guys can work it out. So being connected will imply that you have to have at least n-1, and if you have at least n, then you will have a cycle. Okay, so that's usually how you do this. And also for every 2 vertices, you have exactly 1 path. Okay, so that's another very simple to observe path property of a tree. So every 2 vertices between 2 of them, there's exactly 1 path, because connectedness implies there's at least 1 path, and if there are 2 paths, there is a cycle. Okay, so that's why it's exactly 1 path. So we can restate this communication backbone problem as saying, you have a weighted undirected graph. You want to find a connected subgraph with the minimum total weight. So this is the problem. So you have the full graph is some weighted undirected graph. You want to find a connected subgraph Okay, subgraph that connects all vertices. You want the minimum total weight. And okay, all weights are bigger than 0. So this is the other. Okay, so yeah, so let's try to. So this is a fundamental problem because these kind of connectivity problems arise all the time, right? Like you can imagine like building a network, you want to solve some problem like this or some power grids and so on. These kind of problems keep arising. Okay. So we want fast ways of solving these sort of problems. Okay. And note that the number of trees can be really big. Okay. So exhaustive search is can be huge. Okay. So we want some kind of efficient algorithms for solving these kind of problems. So, alright, so how do we go about this? So suppose we are given some weighted graph, and how do we go about finding a small weight tree? So let's say so you have some weights and you want to find a connecting thing that has the smallest weight. So note that by definition you are interested in small weight edges, right? So you would want to pick the small weight edges. Okay? And I want to make a formal statement of this kind, okay, which will also start off by telling us how do you reason about trees being good. So let me start with a simple claim. Okay. So this is an intuitive claim. So you might think that all I want is some kind of a connected thing, right? So if I look at the edge which has the smallest weight, okay, so can I say for sure that it belongs to the minimum weight spanning tree? Okay. So let's write down this claim. The edge of smallest weight must belong to the main weight, So this claim, you can write this down, but this is not. It seems incomplete because there could be multiple min weight spanning trees, right? So maybe not all of the low weight edges belong to all the spanning trees. Okay, so you might want to revise this claim and say that for every edge, so in this case, let me write it for this graph. Okay, so the minimum weight is weight 1, right? So for every edge of weight equal to 1. Okay, so in general, the claim will be for weight equal to the min weight. There exists a min spanning tree that contains this edge. So is the claim clear? So we are saying take any edge, so of weight equal to the minimum weight. So maybe this edge. Okay. So you have that edge. We are saying that there exists a minimum weight spanning tree that contains this edge. And this is what I want to prove. Okay. So how would you go about proving such a claim? remember there's only one thing we know, right? So about arguing about the optimum. So how would you go about proving such a claim?
Picking up so edges with increasing order of weights.
Well, that's an algorithm, right? So what I'm saying is, I want to prove this claim. Okay, so the claim is for any edge E of weight equal to the minimum weight, then there exists a minimum spanning tree that contains this edge. Okay, so this is just a mathematical statement. There's no algorithm yet.
So,
Yeah.
so maybe you could say that since that edge connects two nodes, or two vertices, if they were connected with any other set of edges, then the cost would be higher. So it would be
Intuitively, that's correct. Okay, so let's, yeah. So
We say there is a better algorithm, and we say that okay, but this is equal to that because in the optimal.
So that's also the right. Okay, so let me formalize this. Okay, so there's no algorithms yet.
Yeah.
Okay, so at this point, what you can say is consider the minimum spanning tree. Okay, so suppose you consider the spanning tree that has the least weight. Okay, so let's do that. Okay, so suppose there is some tree. So I'm not exactly drawing this graph perhaps, but pretend I did. Okay, so maybe this is not exactly the graph, but consider any spanning tree like this. And suppose this is the minimum weight spanning tree, and suppose it does not have this edge. Okay, so I don't know where this edge went. Okay, so maybe I should. So this is this edge. Okay, so this assume this didn't exist. Okay, so suppose this is that one edge that I'm interested in. Suppose the minimum spanning tree is this tree which did not have this edge. Now note that this is a spanning tree, okay, which means every two vertices are connected. Okay, so that's fine. So now you can go ahead, suppose you add this edge. Okay. Now what you know is that there has to be a cycle that is formed. Okay, why is that?
Because it's more than n minus 1.
Okay, that's another way of saying this. Yeah. So, or you could say because it was a spanning tree, every pair of vertices had a path, and now you add this shortcut edge. So now this whole thing forms a cycle. Okay. So that's the other way of saying this. So that's also a good, perfectly fine way of saying this. So you add this edge. This is the edge of weight 1, and now you've got a cycle. But this is the edge of minimum weight, right? So what can you say about all the other edges in the cycle?
They should be equal to 1.
Yeah, they should have weight at least 1. Okay, so they have weight bigger than equal to 1. But now, suppose you cut off any of these edges, okay, and keep this edge. Is the graph still connected? Yeah, you can easily check that it will still be connected because between every pair of vertices there is still a path. Okay. So you've now moved to a new spanning tree. Okay. So this new graph is connected and acyclic. It's acyclic because there was only one cycle to start with and you cut off that cycle, right? So that's why it's acyclic. So it's a spanning tree. Okay, so it's a spanning tree and it has costs smaller than or equal to the previous one. Okay. Smaller than the previous one, which was the minimum spanning tree anyway. So these two must be equal. Okay. And this is the full argument. So this says that cost is equal, and so this proves this claim because what you're showing is there exists a spanning tree that now contains this edge. Because this is a spanning tree that now contains this edge. Alright, so this is a clean observation. So we are saying for any edge of the weight equal to the minimum edge weight, you can always kind of say, okay, I'm going to start building a spanning tree, but I'm going to include this edge. So that's the idea behind what is called Kruskal's algorithm. So the algorithm is basically, it tries to use this fact recursively. Okay, so you know, I want to find a minimum spanning tree. And you know that if I pick any edge of weight equal to the minimum weight, there exists a spanning tree with these two, with this edge. So I can start off by picking that edge, okay, and seeing where it lands me. Right? So I have this graph, and I have this min weight edge, and I have these other vertices, and there is some graph between them. Okay, so for now, let me not care about this graph, but I know that I can pick this edge. So now what do we do with the rest of the graph? Right? So now we had some edges here, this guy had some edges, and we had some rest of the graph. So let's say I picked this edge. Then question is, can you simplify this graph in any way? Okay. So I want to run some recursive algorithm on this, right? So I totally want to pick n minus 1 edges. I say that, oh, okay, I know one edge can safely be picked. Okay, so I pick the smallest edge. Yeah.
You can divide this into two minimum spanning tree problems now.
Oh, how?
So you have the edge between two vertices, so you could say one vertex is in one tree and the other one's in the other tree.
Yes, so that's a good thing, but you don't know which other vertices are in the tree belonging to this guy. Yeah, so that's
it seems like you could, if you eliminated the minimum length edges, you could now say, okay, what's the next lowest available?
So you can try doing that, but the problem is, what you know is that there is a spanning tree that contains each minimum edge, minimum weight edge. You don't know that there's a tree that contains all of them. Okay, so you can't be sure that all the minimum weight edges are part of one tree. For every edge, there could be a different tree, right? So that's the catch. But it turns out what you can do is you can kind of pretend now from now on in this algorithm that these two vertices are actually shorted in some sense. Okay, so they're both just made into one. Okay, so they're just compressed into one vertex because they are connected. You can go from one to the other, and that's all you want, right? So you ultimately want to go from every vertex to every other vertex. Okay, so that's the key idea behind Kruskal's algorithm, where you essentially merge these two vertices, okay, into one vertex. And now you have a bit of a problem, right? So you have edges that go from each of those vertices outside. So these kind of edges like this are okay, because you still have to keep them, okay, and they have same weight. But what about these kind of edges?
Isn't it supposed to be acyclic? So wouldn't those not exist?
Now the original graph can have cycles. It's the tree that doesn't have cycles. So this is actually the full graph I'm talking about.
So would you just discard this bigger one?
Exactly. So you would just discard the bigger one because if you choose to pick one of them, you're not going to pick the bigger one, right? So you'll pick the smaller guy. And you know you'll reach one of them, and from there you can reach the other vertex. Okay, so you throw away the bigger one, and the other guys you just keep there. So you first pick edge of minimum weight, merge the endpoints, cleanup. Perform this cleanup. Cleanup basically means after you merge two endpoints, you form a new vertex and then you connect it to everybody and you choose the edge weights appropriately. Okay, so using what he just said. Okay. And okay, so now you have this new graph. And now you can just recurse. Okay, because this is just another fully legitimate graph. I mean, it's and now you know. Okay, so if I take the minimum edge weight in this new graph, maybe it doesn't involve these two vertices. Maybe it's somewhere else. Okay, so this is now the min weight edge. Okay. And now I can merge these two guys into one node and form this new graph and so on. Okay. And this is it. Okay, so this is what is called Kruskal's algorithm. So from what I said, must be clear, why is this algorithm correct? So suppose I could do this, okay, so I just keep merging these two vertices. Then why is this correct? So the first step I know for sure is correct, right? Because that's what we proved. That there is always a graph, there is always a spanning tree which involves these two vertices. And the next thing you have to show is that going from this graph to this graph is correct. So the next thing you have to prove is any spanning tree on, so let's call this graph G and this graph G prime. On G. So any spanning tree on G which contains this edge E, corresponds to a spanning tree in G prime and vice versa. So this is actually a very simple claim, but I'm just writing it down formally because this is what you've got to prove. Okay, so what we are saying is, I know that the minimum spanning tree in G contains E. Then I'm saying any spanning tree in G that contains E, you can think of it as just a spanning tree in this G prime. And this is why solving the problem here is equivalent to solving it in the original graph. And then it's just induction, right? Because then you can say, okay, you can assume by induction that this was fine, you found the minimum spanning tree over here, and then you can just add that edge E and then go to a minimum spanning tree there. So that's the full proof, and so I'm assuming you proved this, okay? And this is easy to show because, any questions about proving this? So this is actually, it's an intuitively clear statement. I just wrote it down formally. So is that claim clear? Because any spanning tree here, you just add that edge, it will become a spanning tree there. The cost is just the cost of this tree plus the weight of that edge, and vice versa. So that's so this algorithm is correct. One is this claim. So using induction and using this claim one. This so this is very easy. Yeah.
For the second group, so can we say that since we have added E and removed the smaller node, so there won't be any cycles formed and it will still remain a spanning tree, hence it will remain to be a spanning tree.
Wait, what do you mean the second?
So this one, G to G prime.
Yeah. Yeah.
So for that, so can we say that we have added edge for combining two nodes, and at the same time we are removing the other node, which will actually remove cycle.
Okay.
So in that case, the resultant will still remain a minimum spanning tree. So hence,
Well, you don't even need to argue anything about cycles here, because all you are saying is, given any tree over there, I can build a tree in this with the cost being equal to whatever the original cost there was minus the weight of that edge. That is easy, right? And that is still a spanning tree. So also if you start with any spanning tree over here, then adding that edge E will give you a spanning tree there. Okay. And both will be trees because of just trivial reasons. So if you want, you can formally say there's no cycle, but it's, I guess, just obvious, right? It's intuitive. So any other, yeah?
Could you go over the cleanup part again?
The what?
Cleanup.
So the cleanup is basically, so you pick the mid-weight edge, you want to combine these two vertices, the two endpoints into one vertex. Okay. So think of this whole blob that I drew as this vertex. Okay. Suppose I want to do this. Now both those vertices that I am combining have some edges to the rest of the graph.
5 edges.
Yeah, in this case there are a few edges, right? So you have these two guys. There is 1, 2, like this, right? So now I am combining these two vertices into one mega vertex. So the first thing we might want to do is put edges to these guys from this mega vertex to the ones that have only ones that are connected to only one of these two. And that you will put the same weight. Okay, so if the weight is W here, you will put W here. Okay. So also to these guys. Okay. Whatever this weight was, this weight will be the same.
So in case they had a common point, then you take the minimum.
Yeah, if they had a common thing, then I can take the minimum because I ultimately want to prove that claim, right? Okay, so that's the reason. Alright, so it's good to clarify this thing. So, yeah, any other? Okay, so this algorithm is correct. So how long does it take to implement this? Oh, I didn't realize I had a full slide. Okay, so how would you implement such an algorithm? Note that it's the way we described it, it's a little bit messy, right? You have to, every time you pick two vertices, you have to merge them, and then you're doing something to the edges. Okay, so how do you do this quickly? So how to implement this cleanup or merge? So here I will, so I'll draw your attention to two aspects and then I'll let you figure out the details. Okay, so actually the first thing is you have to be a bit careful. Okay, so that's basically your vertices, they'll start off by just being two vertices in the original graph. Then soon you could have done multiple merges for a single vertex. Okay, so that's something you've got to keep in mind. So a vertex at a later stage corresponds to a set of initial vertices, subset of initial vertices. So this is one thing. So you've got to figure out an easy way of maintaining that. Okay, so you can always keep introducing vertices, but still. Okay, so, and how would you implement this cleanup phase? So what's the easy way to implement this merge? So the naive way takes time which is proportional to the sum of the degrees, right? Because you'll form a new vertex, and so these are the guys being merged. You form a new vertex, and you'll look at all of these things, and you'll add new edges from that new vertex to these guys, right? But turns out that's a little bit inefficient, because let's say this set of initial vertices. So each vertex at a later stage corresponds to a set, and suppose the set has a larger size, okay, then the degree of this node keeps growing, right? So every time you don't want to pay the price of the degree of the old nodes multiple times. Okay, so this is the thing that you've got to keep in mind. So it turns out there's a way to do it so that you always do number of operations to be roughly equal to the degree of the new node that's being added. Okay, so I haven't defined exactly what this means, but this is something I'll just leave you to figure it out. Okay, so it's there's a clean way of doing this so that you don't keep repaying the cost for what it took to add some more node. So this is what you've got to do a bit more carefully. And so again, so this is the merging step, and then there's also this step of finding the edge of the smallest weight. This, it turns out, you can do the same trick as Dijkstra. Okay, so you can just keep a priority queue. For the edges, and then in this stage you have to figure out how these two interact. Okay, so it's yeah. So, but you can always. But it turns out you can do this with final runtime m plus n times log. So the log n comes because of the priority queue, and the m plus n comes because essentially every time you merge, you pay only the degree of some true vertex. Okay, so that's the idea of this. Okay. So is the rough idea behind the analysis clear? You have to figure out how to implement these details well. Okay, but it turns out this can be done in time O of m plus n. So I wanted to do one other. So I'll let you guys figure out the details of this Kruskal, the final step. But I wanted to do another very natural algorithm for spanning trees, which is actually even simpler than this. Okay, so that's why I don't want to do the full analysis of this. So this is nice. It was based off this intuition that the minimum edge you can always assume exists in the graph, exists in the spanning tree. But now we can try a even more simple greedy algorithm, right? So that's what is called Prim's algorithm. So what it does is, you have this graph, you start off with any node, okay, so let's say you start with this guy. Okay. And what it does is, it starts building a connected component. Okay. So imagine, so ultimately you want to have the whole graph as the connected component. It starts building this connected component one by one. Okay, so what it does is, initially you have the connected component is just one vertex. Okay. Then it picks the smallest edge that goes out of this component. Okay. In this case, what's that edge? 4. This is a 4. Okay. So it picks this edge. Okay. Now this is the component. Okay. And now you have the 6 and 13, 11, 3 and so forth. So now 3 is the smallest edge that goes out. Okay. So we end up picking this guy. Okay. So now the connected component consists of this whole thing. and you keep growing like this. So this is start with the vertex and add nodes greedily, actually I should say nodes, greedily to the connected component. So here there are no implementation issues, right? All of you can just implement this trivially. Turns out this also gives the right answer. Okay, so the theorem is that this algorithm finds a minimum span. So I was hoping to do this also, but maybe we'll see this next class. Okay, so we'll see the proof of this. And next time I also wanted to, so the running time of this you can easily analyze. So this also has the same kind of a running time. So it's n plus n times log n. And here again the running time is because here it's even easier, right? You just maintain some priority queue and you keep adding edges to this priority queue. Every time you pick the earliest one, then you throw away vertices that were, yeah. Okay. So it's easy to check. So the correctness we'll see next time, and next time we'll also introduce this very nice notion of cuts in graphs. Okay, so we'll consider this min cut problem.